Hello everybody, this is Dr. Christopher White, and in this video we're going to be looking at exercise 16 from Interpreting Earth History by Ritter and Peterson. Okay, so we're going to want to start by turning to page 240, on which we're going to find exercise 16, shock horror. So exercise 16 focuses on the Cordilleran orogeny. So if you remember, the Cordilleran orogeny is three separate orogenies: the Nevadian, the Sevier and the Laramide orogeny, and those three orogenies combine to give us the Rockies. So you'll be very happy to know that exercise 16 does not involve you drawing any cross sections. So yay. It does, however, require you to analyze geologic maps. So what we're going to do is we're going to look at geologic maps, and you're going to be analysing things like how deformed are the rocks, what time did that deformation happen, and which one of the three orogenies is the most likely cause of that deformation. So exercise 16 obviously starts with the learning objectives, just like every other exercise, and then we have the introductory text here starting on page 240. Once again, please just take a second and read it. It's full of very good information. So it starts on 240. Now on page 241 we have a very good diagram showing the broad regions affected by the Nevadian, the Sevier and the Laramide orogenies. I would like you to take note for just a second that the Nevadian orogeny is associated with a lot of intrusive activity. And that's because the Nevadian orogeny is kind of the classic ocean-continent convergent boundary, where you end up with a mountain range, and that mountain range is stuffed with volcanoes. Think kind of like the modern-day west coast of South America now. And obviously these volcanoes need magma to feed them, and this magma is of course emplaced into the crust as magma chambers. Those magma chambers will eventually solidify and give us lots and lots of intrusive rocks. So Nevadian is commonly associated with lots of intrusive activity. Then of course we have the Sevier thrust fold belt, and of course this is a region where we have a lot of tectonic deformation, mostly in the form of thrusting, so sheets of rock are being pushed one over the other. And then further out here we have the Laramide Belt, and this essentially is a region that's deformed mostly by normal faulting. And I stress mostly by normal faulting, and that means in those areas we tend to have large blocks of rocks being pushed up. It's not exclusively normal faulting though, there is some thrust faulting in there as well. So this diagram kind of gives you a broad overview of where these belts actually occur. I should point out as well, here we have what's referred to as the foreland basin, and this essentially is a region into which the sediments being eroded from the high ground are being deposited. So we have a continuation of the text which you saw on page 241, and then at the bottom of page 242 we have a really good diagram of the foreland basin associated with the Sevier orogeny. So you can see over this side we have the elevated ground, essentially the mountains/hills produced by the Sevier uplift. And you can see this sediment essentially is being eroded off this high ground, and it's being deposited into the basin. Now this obviously means we have coarser material closer to the high ground, and as we go westwards the material steadily becomes finer, so we have conglomerates going into sands, going into muds. You'll also notice that we have essentially a down warping of the crust associated with this region of the basin itself, and this is typically because you get large quantities of sediment being deposited into this area. It puts the crust under a lot of stress, and it will literally start to pull it down, or should I say push it down. And so this produces a depression, and of course the more sediment you pile in, the greater this down warping becomes. So then on page 243 and page 244 we have photographs of key rock layers associated with the Nevadian, the Sevier and the Laramide orogenies. And then on page 245 we have a geologic map essentially of the Bighorn Mountains in Wyoming. So what's actually been produced on this map is, we can see, well, it's a bit of a complicated map. Mostly on this side we have lots and lots of stuff which is referred, has letter codes of Q, that means quaternary, so it's quite young material. And then over here we have ourselves a lot of material, so we have some stuff which is M, so that's going to be Mississippian. We have stuff that's, what have we got? We've got stuff that's O, that's going to be Ordovician, and we have stuff that's C with a line for it, that's going to be Cambrian. So right here we have ourselves a thrust fault. And so if we were to take a section through this, and they've actually drawn one for us between A and A prime, what we're going to see is that the rocks on this side of the fault have been pushed over the top of the rocks on this side of the fault. So what we've ended up with is we've ended up with the older Mississippian, Ordovician and Cambrian in contact with much younger tertiary sediments, or should I say tertiary sedimentary rocks. So this is the classic sign of a thrust fault. We have essentially much older sediments, well, sedimentary rocks, should I say, being pushed over the top of younger material. So bear that in mind, because that's going to become important later on. I should also point out, and I'm sure you remember this, that thrust faults are essentially lines with triangles on them. That's how we put them on maps. And remember, the triangles always point in the opposite direction to travel. So you'll notice the triangles in this case are pointing, in a kind of southwesterly direction, aren't they? However, the direction of travel of this piece of rock is to the northeast. So they're pointing to the southwest, but this block of rock here is moving northeasterly. So just bear that in mind. That's something you always need to remember. The triangles point in the opposite direction of travel. And once again, that's going to become important later on. Okay, so part A. What have we got for part A? We'd be happy to know part A is a relatively straightforward opening. So part A, question 1. So we're going to look at the geologic map provided on page 248. So here we go. So this is the geologic map provided on page 248. And I think the first thing you're going to notice is that is a lot of pink, isn't it? Now, pink on geologic maps will very often mean igneous rocks, more accurately plutonic igneous rocks in most cases. So what we can see here is we have numerous shades of pink and kind of pinky purples. Okay, these are going to be plutonics. Okay, so intrusive rocks. So what we can see here is we have an area that's absolutely stuffed with intrusions. Okay. So, question 1. So look at the geologic map. What rock type predominates in this map area? Oh, I've kind of given that away, haven't I? Intrusive igneous, extrusive igneous, sedimentary, or metamorphic? Well, you can answer that one, can't you? Question 2. What is the difference between granite and granodiorite? So one of the things you'll notice is that most of these intrusive rocks are either granite or granodiorite. And so what's the difference between them? Well, that's one for Google. Question 3. During which geological period, did the majority of these igneous bodies form? Well, in order to answer that, we can come over here to the key. Okay, so what's the key going to tell us? Well, the key tells us the letter codes associated with each layer of rock. Now you'll notice how the letter codes are consistent. So in this case, we have JMS. That means J means Jurassic. So just out of the field of view. Okay, then we have a whole range of rocks here where the letter code starts with K. K means Cretaceous. And then we have a range of letter codes up here that start with Q. Q means Quaternary. So the letter code at the start gives you well, normally will tell you what period your rock was deposited in. So okay, so when you look at this key here, you're going to notice that there is one period in particular which dominates over the others. Okay, so one period is where most of the rocks were formed. So you should be able to, work that one out pretty easily. So question 4. What evidence of multiple episodes of intrusion in the Sierra Nevada is shown on the map? Okay, here we go. So here's our map again. Now, if it was just one intrusive event, what would you expect to see? So if it was just one huge intrusion, well, obviously you would expect to see just one type of rock, wouldn't you? You know, a whole load of granite, a whole load of granodiorite, and it would of course be totally homogeneous. All right. So, does this map look homogeneous to you? Well, you'll have to answer that one yourself. But, you know, once again, if it was just one event, then you would expect, you know, the map to look pretty uniform. But it doesn't, does it? So you're going to have to think to yourself, is this a homogeneous map or a heterogeneous map? And if it's a heterogeneous map, well, maybe that would suggest that it just wasn't one event. But once again, think about it. You know, take a second, draw your own conclusions. Question 5. What was the source of the magmas that solidified to form these igneous bodies? Well, we're dealing with felsic and intermediate magmas, aren't we? So felsic magmas will give you a granite, intermediate magmas will give you a granodiorite, or felsic / intermediate magmas will give you a granodiorite. So, question then becomes, where are these magmas coming from? Well, I'm not going to tell you, but I would advise you to go back to the tectonics lecture and maybe spend a couple of minutes just having a look at the continent-ocean convergent plate boundary. Okay? And that will give you a bit of a hint about what's actually melting to form these, you know, more felsic and intermediate magmas. All right. So, question 6. What is the nature and significance of the Paleozoic rocks in the lower left portion of the map? Right. So if we go back to our map here, what can we see? Well, obviously we can see this whole area here is just stuffed with intrusions, and then down here we have this green area in the bottom left. Okay, so what's this telling us? Well, always remember, if you are having, if an intrusion is intruding the crust, obviously you need some crust there for it to intrude. So whatever, you know, crust it's intruding, obviously by its very nature must be older than the age of the intrusions, mustn't it? So I think you can probably work out, you know, what that is. By the way, there's a term we use for rock that's, you know, typically being intruded, and we typically refer to it as the country rock. Then question 7. What is the name of the orogenic phase of the Cordilleran orogeny that most greatly influenced this area of California? Okay, well, we have 3 of them to choose from: the Nevadian, the Sevier, and the Laramide. Okay, so what we're going to do is we are actually going to have a look at something I put together earlier. So we're going to jump over to my computer screen. Here we go. And I'm just going to make this bigger. There we are. Okay, so here we can see we have ourselves a map, well, the geologic map of North America produced by the USGS. It is a thing of beauty. And over here on the left, of course, we have ourselves a geologic timescale. So what can we see? Well, we can see that I've marked onto this map the major orogenies that occurred in North America, and I've given the time range for each of the orogenies. So we can see the Nevadian, essentially Middle Jurassic to Early Cretaceous. Now, the one thing I will point out is that these ranges here, okay, are the periods that the orogeny was at its strongest. Okay, obviously there's going to be a build-up and a cool down after the orogeny. So don't just think, you know, the orogeny stops hard in the Early Cretaceous. It would continue for a little bit afterwards. So just please bear that in mind. So the Nevadian orogeny, Middle Jurassic to Early Cretaceous. Sevier orogeny, Middle Jurassic to Late Cretaceous. And the Laramide orogeny, Late Cretaceous to Paleocene/Eocene. Okay, so we're dealing with rocks which are mostly Cretaceous in age. So, you know, any 3 of these would do. Okay. Now, the one thing I'd ask you to do is have a look at the location we are dealing with. Okay, so I'm just going to quickly jump back to the textbook. All right, so we are in California, so we are right here. Okay, so now we're going to jump back to the screen. and so that would make our approximate position would be somewhere about here, maybe, give or take a little bit. Okay. The other thing I would note is that our map is full of intrusive rocks. Now, I spoke earlier, one of these orogenies is associated with lots and lots of magma movement. Okay. So the age of the rock, yeah, that's acceptable with the age range for that particular orogeny. The location and the large amounts of intrusive rocks would be consistent with that particular orogeny. So I think you can probably work out which orogeny it's most likely to be. Okay, so that's the end of part A. So I think we can agree that was all relatively straightforward. All right, so let's jump back to the textbook. And on to part B. I don't know whether you can hear, but my little dog Rupert is going absolutely berserk in the background. Okay, so part B. What are we dealing with now? So in part B, we are looking at the Lake Minnewaca quadrangle of Alberta, Canada. So as you can quite clearly see, we've moved north of the border, and this is our location here. Okay, so where is our map? Well, to begin with, you can see we have a much more extensive key this time. Okay, it covers 2 pages. Now, because the map is far more complicated than the map we just saw a second ago, we still have the letter codes, but now we also have the addition of a description of the color that each of those rock layers has been given, and we've also got a description of the rock type for each of those layers. And this is our map here. So it's designed to be in portrait, so here we go. So it's not going to quite fit on the field of view, I'm afraid, but I don't really want to adjust the camera too much. So you'll spot relatively quickly that this is a bit of a complex map, isn't it? Well, we can see quite clearly that the layers of rock have a very convoluted appearance, don't they? So you know that might become important later on. We can also see that we have several frost faults in the area. We've got a big one coming down here. We have another one running down here. And we have a smaller one down here in the bottom left. Okay, so we've got a lot of frosting going on. We also have a line running down here. You might be able to see it. This line has 2 arrows pointing towards each other, which is, of course, I'm sure you'll remember, the map sign for a anticline. And next to it, it has a line coming down here, which has arrows pointing away, which is the... no, wait, I've got that the wrong way around, haven't I? Arrows pointing towards each other is the map symbol for a syncline. Arrows pointing away from each other is the map symbol for an anticline. Whoa, what an amateur mistake that was. So yes, so these lines are telling us we have ourselves a syncline running down here, and an anticline running parallel to it. So we have a syncline-anticline pair, which is, you know, what you would normally expect to get. What we can see, though, is this particular anticline is actually cut by the later frost fault. So that's quite interesting there. You can see how the anticline stops and reappears several times because it's being, you know, because the frost fault, is coming over the top. Okay, so as we can see, this is a bit of a complex area. All right, let's have a look at the questions and see what's going on. So, question 1. So see the geologic map we just did. Generally characterize the rocks shown on this map as to their age and rock type. Okay, well, we don't actually need the map for that. What we need is the key. So we can see on this map we have Cambrian rocks, Devonian rocks, Mississippian, Pennsylvanian and Permian, Triassic, Jurassic, Cretaceous, and even some Quaternary stuff. So we're covering quite a lot of the geologic timescale here. Okay, so the question is, well, when did most of these rocks form? So don't start giving me individual periods. It says generally, so that means Paleozoic, Mesozoic, Cenozoic. All right, did most of the rocks form in the Paleozoic, the Mesozoic, or the Cenozoic? So that's relatively straightforward. Now then it wants to know, well, what type of rock dominates? All right, so which one type of rock kind of pops up quite a lot? All right, so I think you should be able to work it out pretty easily, because there really is one type of rock that really is extremely common in this particular sequence or sequence of rocks. Okay, question 2. So characterize the structure of the area as gently, moderately, or complexly deformed. What type of structures are present? Okay, well, I'm going back to the map for this one. So we need to say, right, have the rocks in this area been deformed? Essentially lightly, moderately, or, quite a lot. So obviously, if an area has been gently deformed, you would expect to see maybe some, nice, gentle, open anticlines and synclines. Maybe a few small faults. The layers of rock might be, folded. It might be, might show minor signs of having been folded, but on the whole, you really wouldn't expect that much, would you, if it's been treated quite gently? So I think we can agree quite quickly that this is definitely not an area that's had a gentle geologic life. Now, that obviously means, it hasn't been treated. Is it an area that's, had moderate deformation or quite strong deformation? So, this one is going to be a little bit tricky. So, one of the things I will say to you is that although this map looks rather complex, remember that a lot of this complexity that you're seeing here will actually be the result of topography. Okay? So, some of the stuff we're seeing here is actually, the result of how the rocks are exposed on the surface of the Earth. So, just bear that in mind, just a little bit. So, it's not all to do with how the rocks are actually, deformed or how the rocks actually look. Some of it is, how they're exposed on the surface of the Earth. Now, I would point out a few things, though. So I would point out that over here, we clearly have ourselves quite a large fold, don't we? You can see that we have, closing up, essentially, in this direction. You can see we have the same repeating units on either side. So it's just like the anticline or synclines we were dealing with, in the previous lab. So what can we see? Well, in the core of it here, we have what would appear to be, I'm just going to double check it myself. Yes, we would appear to have Devonian age rocks in the core. And we would appear to have Cambrian age rocks out here on the edge. So we have younger rocks in the middle and older rocks on the outside. So of course that's the classic sign of a syncline. So we have ourselves a syncline right here. It's not actually marked on the map, but we can see it's there nevertheless. And we can see we've got another fold up here. Once again, we have younger rocks in the middle and older rocks on the outside. So we have ourselves another syncline there. And then we have some kind of feature here that looks almost like it might be a basin or a trough of some kind, maybe not. But we also obviously have ourselves our anticline-syncline pair over here. We have 1, 2, 3 very large folds and a few frost faults, and a few lesser frost faults also knocking about on the map as well. So it's a matter of personal opinion, but we have a sequence of rocks which is showing, yes, pretty common folding. We also have a sequence of rocks which is showing that they have been deformed in a brittle fashion as well, so there is quite a lot of frosting here. So, it's your decision. Has it been moderately deformed or has it been strongly deformed? Obviously, what type of structures are present? Well, you can work that out from what I was just saying. So, question 3. In which direction did the frost faults move? How does this fit the plate tectonic model? Okay. Well, I was speaking earlier about how the triangles show you the direction of travel. So I'm not going to tell you how they're moving. I hope you should be able to work that out for yourself. Now, what about how does this fit with the tectonic model? Well, I'm just going to go back a page, or 2 pages actually. Okay, so this is North America. So if you remember, during the well, during the time of the Caledonian Orogeny, not Caledonian Orogeny, I do apologise, Cordilleran Orogeny, and still going on now, in fact, North America is moving westwards. Now this means you have a piece of continental crust overriding a piece of oceanic crust. So we have ourselves a ocean continent subduction zone, or at least we did. So this means that we have two pieces of rock banging into each other, okay, which produces quite a lot of stress. So it produces forces pushing into the United States, okay, well, into North America in general. And so this means we're going to have a force which is going to be pushing from the west going towards the east. Okay, so how does that kind of force, this kind of eastward pushing force, so coming from the west and going towards the east, how does that fit with the direction of travel that you just come up with for those thrust faults? So are the thrust faults moving in a relatively similar way, or are the thrust faults moving in a different way? Are they moving in the opposite direction, for instance? All right, so if they're moving in approximately the same direction, then there we go, that's consistent. If, however, they're moving in the opposite direction, well, that's not consistent, is it? We've got to come up with another explanation as to why that would be happening. So have a look at the major thrust faults. We said there are 3 of them on the map, and have a look at their direction of travel and just see whether that kind of matches with this, west to east, compressive force, which would have been the result of a very large subduction zone running along, nearly the entirety of what is the modern day east coast of North America. Of course, as we know now, most of this has now changed. We have a transform plate boundary down here, transform plate boundary up here, and the only subduction left is around here, Northern California, Oregon, Washington State, and southern British Columbia here. That's the only area that now has any subduction taking place. But once upon a time, we had a subduction zone that ran all the way down here, like so. Okay. So, question 4. What is the likely age of deformation? What is the evidence for your answer? Okay, well, a very basic concept that a lot of people seem to not quite grasp is that if you want to deform something, it has to be there before you start deforming it. Kind of common sense, really, isn't it? But a lot of people forget this very, very basic idea. So what we've got is we have ourselves a whole pile of Paleozoic rocks. So we have some Cambrian rocks, some Devonian rocks, some Mississippian rocks, some Carboniferous rocks, and we have a few Permian rocks as well knocking about. So we have a big, thick sequence of Paleozoic rocks, and we can see those Paleozoic rocks have been, deformed, quite a lot. Now, then we also have some Mesozoic rocks. So we have ourselves some Triassic rocks here. These green rocks, they're Triassic in age, and we can see these are part of the syncline. Now, is there anything else knocking about? Do we have any Jurassic rocks around in this area? Well, let me see. Anything that looks Jurassic? No, I can't see any J's. I think there was a J mentioned in the key. Yeah, there is a Jurassic rock knocking around somewhere. Dark blue-green. Let's see. Dark blue-green. Well, can we see that anywhere at all? Oh, what am I? Silly me. It's right there. Hold on. It is right here. It's this layer of rock coming down like so. So we also have that. So, okay. So what have we got going on? So we need to try and work out which one of the 3 orogenies it is. Nevadian, Sevier, Laramide. Now, once again, you can remember straight away that one of those 3 orogenies has a lot of thrust faulting associated with it. So that might be a hint as to what's going on. So our next thing is we need to try and see what's going on. So we can see that the Triassic rocks are deformed. We can see that the Jurassic rocks are deformed. So it's being cut by a thrust fault right here. Okay. So it's being cut by a thrust fault, and we've got Triassic rocks coming over the top of Jurassic rocks. So younger going over the top of, sorry, older going over the top of younger. Of course, classic sign of a thrust fault. Okay, so that's good. Thrust fault here, thrust fault there, thrust fault coming down here. Oh, and this, yeah, so thrust fault, thrust fault, thrust fault, and thrust fault. It's all going on. So is there anything else that's deformed? Well, right up here at the top, which we're going to bring down into shot. Okay, dark green in colour. Hasn't got a letter code, but we can see it is surrounded by a thrust fault. So it too has been thrusted into the area. So let's try and see what that is. Dark green in colour. So dark green in colour is going to be Cretaceous. Here it is. Okay, so this is a Cretaceous rock that's clearly also been thrusted into the area as well. So clearly the deformation was going on in the Cretaceous as well. So, okay, what, do any of our three orogenies work, with this model that we've put together? So we've got a model that says that whatever's doing the deformation was deforming definitely, after the Cretaceous, or Cretaceous and later. And we also know that whatever was doing the deformation was very, very prone to producing thrust faults. Okay, so what we're going to do is we're going to go back to my computer screen. Here we go. And we're going to look at what we've got. So, right, we've obviously got North America again. Now, obviously, we're not interested in the eastern seaboard, so we're over here. So we have the Navajian orogeny here, the Sevier orogeny. Sorry, that's the Antler orogeny. I do apologise. The Sevier orogeny is marked out here in purple, and the Laramide orogeny is marked out in white. Okay, so the first thing is, well, where are we in the world? Well, of course, we're up here in Alberta. Okay. So that's going to put us somewhere in this kind of region here, where you're kind of close to both the Sevier and the Laramide, so that's not really going to help us very much. All right. So let's just try and think, though. We can see that both the Sevier goes to the late Cretaceous, and the Laramide starts in the late Cretaceous. So both of these orogenies would be capable of thrusting and moving around, Cretaceous rocks, which are early Cretaceous and middle Cretaceous. Okay, well, the middle Cretaceous doesn't actually exist, but you get the idea. It has the capacity to move around rocks which formed in towards the earlier portions of the Cretaceous and towards the middle portions of the Cretaceous. Okay, the one thing that we don't have in this key is, unfortunately, we don't have an age for the dark green rock, so unfortunately we don't really know whether it was early or mid Cretaceous in age. So both the Sevier orogeny and the Laramide orogeny have the capacity to have deformed these rocks. In fact, so does the Navajian orogeny. The Navajian orogeny is still going in the early Cretaceous, but the one thing that you will notice when we look at this map is there's a rather distinct lack of intrusive bodies, isn't there? There's not much by way of igneous stuff going on, so that's probably a bit of a hint as to whether the Navajian orogeny is involved. So, okay, so you've got to think to yourself, is it Sevier or is it Laramide? So, think about the age of the rocks and think about the way in which the rocks are being deformed. Okay, so I discussed right at the beginning that those two particular orogenies, the Sevier and the Laramide, have a rather different way of deforming the rocks. Okay. So yeah, so what's the evidence for the likely age of deformation? Okay, what's the evidence for your answer? Well, we worked that through. And then question 5, which phase of the Cordilleran orogeny is represented by deformation in this map area? So once again, we've already worked through that. Okay, so we have been going for about over 30 minutes, so cripes. That's a bit longer than I was hoping for. So this would be a good place to stop this video, and we'll restart in a little bit. So once again, as usual, get up, have a walk around, get some water, tea, coffee, have a snack, and then come back when you're ready for the second half.